Quick question for you. Why don't you fall through the chair you're sitting on right now? Sounds kind of dumb, but recall that most of matter, even the chair you're sitting on, is empty space. So there's no reason in principle that your body and chair couldn't occupy the same space. Why don't you? Well, it turns out that the chair and your body are coated in electrons. And they're all negatively charged. And two negatively charged things repel each other. So it's actually the electric force that keeps you from falling through your chair. That's the topic of this lesson. We'll learn all about the electric force, about how like charges repel each other, and how opposite charges attract each other.
Let's begin by reviewing our lesson objectives. First, we'll introduce electrical charge. Then we'll introduce the electrical force. And lastly, we'll calculate the electrical force. You've probably had this experience before, your hair standing up on end. Here's the interesting thing though, is gravity wants to pull that hair back down. So there's some force fighting gravity and actually beating it. It's stronger than gravity. What force is that? Well, it's the electrical force. You can replicate this hair standing on end situation by taking a balloon and rubbing it on your hair. Electrons, small little charged particles, hop from your hair to the balloon. This makes the balloon negatively charged and your hair positively charged. And well, opposites attract. This same attraction is at the heart of the hydrogen atom and all other atoms. In the center of atoms are protons. They're positively charged. Orbiting around them are electrons, and they're negatively charged. Because of that opposite charge, they're attracted as well, and they stay together. Remember, atoms are made of protons and electrons. They have opposite charges, and opposite charges attract. So if we have a positive and a negative charge, they will move towards each other. On the other hand, like charges repel each other. So two positive charges, like say two protons, will push apart from each other. And the same effect can be achieved with two negative charges. They'll also repel each other. That actually contrasts with the gravitational force. So here we have the moon and the earth, and they're attracted to each other because of gravity. But gravity is always attractive, whereas our electric force is just sometimes attractive. So here's our hydrogen atom, and it's being held together because the charges are opposite. But if the charges were the same, they would repel each other. On the same topic, comparing the electrical force to the gravitational force is somewhat interesting. Here, the hair on this woman's head is sadly sticking straight up. That means that every single hair would prefer to stand up from the electrical force than to fall down from the gravitational force. And that's because the electric force is much, much stronger than gravity. So the electric force is much, much stronger than gravity. Let's take a look at the equation we can use to calculate the electric force. It actually looks quite similar to the one we use to calculate the strength of gravity. Here we have F, which stands for force, and we would use newtons here for the unit. The Q's are about charges, so Q1 is just charge 1. And we measure charge in coulombs. So charge 1, and we're going to measure that in coulombs. This is charge 2, and we'd also measure that in coulombs, abbreviated with a C. On the bottom is the distance between the two charges, and we'd use meters to measure that distance. Up front, the K is called the Coulomb's constant, and it's equal to 8.99 times 10 to the 9th newtons meters squared per coulomb squared. Wow, that is a lot of units. Constants like this often get a lot of units, and we'll actually take a closer look at just why it has this units in a second. The last thing to note here is that this equation actually only calculates the magnitude of the electric force. And so for that reason, it's best to put those vertical bars there around the F and the charges. It won't tell us the direction. That is, it won't tell us if it's attractive or repulsive, or what direction it's pointing in. So it's only going to tell us the strength, the magnitude of that force. Okay, let's take a closer look at the units for this equation.
All right, let's take a closer look at the units of this Coulomb constant thing, because they were pretty messy. Remember that eventually we want force to be in newtons. And our K, if you recall, is in newtons times meters squared divided by Coulomb squared. So a lot of stuff going on there. Here's the thing though.
If we think about it in the context of our equation, it starts to make a lot of sense. Remember, up top in our equation, we have Q1, it has the units of coulombs, and we have Q2, also has the units of coulombs. On the bottom, we have the distance squared, which is going to give us meters squared. So notice that one of our coulombs cancel when we plug in all of our units, then the second coulomb cancels, and both of our meters cancel out, leaving us with just newtons. So this K thing here just takes on the units it needs to connect all of these charges and distances with the unit newtons. This problem says a positive point charge with a charge of 2.2 microcoulombs. That's right, that weird little U thing there, it's a Greek letter, the Greek letter mu, and it stands for micro. So with a charge of 2.2 microcoulombs is 0.2 meters from a negative point charge with a charge of minus 1.8 microcoulombs. What is the magnitude of the electric force between these two particles? And then lastly, is it attractive or repulsive? Okay, well, let's begin by writing down the variables we know. We know the distance, and that's going to be 0.2 meters between those two charges. We also know our Coulomb constant, so that's nice. We already have that written there. Q1 is going to be 2.2 microcoulombs. And Q2 is negative 1.8 microcoulombs. Okay. Now, before we can use our expression to calculate the strength of the electric force, we actually need to go ahead and convert to regular old coulombs. So let's do that. We're going to divide by microcoulombs and go to coulombs. Coulombs is going to go with the number 1 and micro with 10 to the 6th. The microcoulombs are going to get canceled out. And when we do 2.2 divided by 10 to the 6th, we'll get 2.2 times 10 to the minus 6th coulombs. Same basic procedure here for the minus 1.8. We'll do times 1 coulomb over 10 to the 6th microcoulombs. And we'll get minus 1.8 times 10 to the minus 6th coulombs. Okay, now we have our charges, and we need to calculate our electric force. So let's do that. Our electric force is going to be equal to K, which we know is 8.99 times 10 to the 9th, times our first Q. Remember that we have these magnitude bars, so we need to remove any signs we have in our Q1 and Q2. If they're negative, we just need to make them positive. Our first Q1 is already positive, so we can just go ahead and put times 2.2 times 10 to the minus 6th. But our second charge does have a negative sign on it. So the magnitude of Q2 is actually going to be just removing that minus sign, and we'll have 1.8 times 10 to the minus 6th coulomb. So when we plug that in, we just put 1.8 times 10 to the minus 6, and our sign is gone. Because remember, here all we're calculating is the magnitude of that force. Then we divide by the distance squared, 0.2 squared. Okay, that's a whole lot to put in your calculator. This is another situation where it's a good idea to go ahead and give that a try. So go grab your calculator and plug in all these numbers. 8.99 times 10 to the 9th, times 2.2, times 10 to the minus 6, times 1.8, times 10 to the minus 6. That's a lot. Go ahead and click enter, and then do divided by 0.2 squared. We should get 0.8900. When we round for our sig figs, we should keep in mind that the distance just has one sig fig, and that means we'll round to 0.9 newtons. So that's the force between these two point charges. Lastly, we were asked if it was attractive or repulsive. Well, keep in mind these charges are opposite, so it's going to be an attractive force between these two point charges. All right, now it's your turn to practice. Two positive charges, one with 1.7 microcoulombs and the second with 3.2 microcoulombs, are separated by 1.3 meters. What is the magnitude of the electric force? Is it attractive or repulsive? Pause the video and see if you can answer these questions. Okay, first we should calculate the force, and we'll get 0.029 newtons. That's the strength of the electric force between these two charges. Is it attractive or repulsive? Well, notice in this case, both charges are positive, so that's going to be a repulsive force. Let's review what we've learned. First, we introduced electrical charge. We saw that charges come as negatives or positives, and they're at the heart of what makes up atoms. Then we introduced the electrical force, where we saw that negative charges repel each other, positive charges repel each other, but a negative and a positive, that gives you an attractive force. Then we calculated the electrical force.
Hey, hey.